So I'm giving this talk on behalf of Océane. She made most of the work that I'm presenting here. And you will see that most of the presentations today were working on the sample. Now we move from very far away because we're speaking about a flyby that happened almost 1 million kilometers far from the moon. And let me introduce you the lab. So we speak about our lab in DLR Berlin. We have 3 spectrometers all the same time. So it's a spectrometer that works in vacuum. And we have a very wide range of detectors. So we cover from UV to the far infrared. And of course, we just manage detectors and we split combining them together to cover the spectral range together with lamps. And so we can really do spectroscopy on a huge spectral range. And more than that, we have even a very broad offer on methods. So we can do hemispherical, biconical, bidirectional, and emissivity. So emissivity is a little bit our star product. And because we have a chamber, of course, you need to have some external chamber to do emissivity, and the chamber we have built to go in vacuum and to reach high temperatures because we wanted to do mercury studies, and it happened to be very reliable for lunar samples measurements for Venus too. So it's very flexible. We can do a lot of experiments there. And so the scheme of this work, what we did is we have a lot of lunar analogs. We started characterizing them as fresh. So we took hemispherical reflectance on the samples fresh, and then we put the samples in the emissivity chamber, and we in vacuum heated them to lunar temperature, so 130 degrees. We took emissivity measurements on the samples, and then when the samples cooled down, we took out of the chamber, and we could do hemispherical on the heated sample. So we sort of have emissivity on the heat one, and hemispherical on the fresh, and heated we can have a sort of controlling on the samples on the spectral features. We had some samples, some simulants, Apollo 16 and some Mojave Desert sands. This is in 2 grain sizes, so we don't have grain sizes for most of the samples, but in this case, yes. An Eiffel Sun simulant, and DLR Lunar mixture is a sample that I made following the Apollo 16 mineralogy. And in this case, I could mix several grain sizes. So here we have 4 grain sizes. You will see the grain size information on this sample. Lunar Highlands simulant and Lunar Mare simulant from JC. And this Highlands and Mare is very important point you will see when I will speak about the MERTIS observations. So this is a hemispherical reflectance that we took. You can see on the left panel, this is heated and fresh. You can already see that there is a difference. So when you heat up the samples, there is a trend in making the sample darker. So the 1- is higher because, of course, the sample has lower hemispherical reflectance. We show 1- because 1- is almost similar to emissivity. Since the main product is emissivity, you will see something closer to that. And here on the right panel, you will see the comparison of the different grain sizes. So you see grain sizes as an effect. It's not huge, but it's especially when you jump from the very fine to the intermediate and larger grain size, you see that there is really, especially in the radial bands region, there is a huge difference. So before and after heating, you will see that there are some trends. Most of the time, we have a shift in the Christensen feature, and this is not constant. There are some examples where the shift is going to the lower wavelength ranges and sometimes to the larger wavelength ranges. But something that you can notice is that the radial bands after heating. So this is again is hemispherical, so taken at room temperature on the sample fresh or after heating, but in any case it's everything at room temperature. You can see that radial bands increase a little bit in the contrast. So this is an important factor. Let's speak about emissivity, because as I told you, this is something that really correlates to what we observe with MERTIS during the flyby on the moon. And of course, it's very straightforward to notice that when you have a finer grain size, the Christensen feature is showing this very narrow feature. So it's very arrow-like feature, and you will see even this very this large difference between the position of the Christensen feature in emissivity and the lower part of the spectra, so the Australian band here. So this is something that has been already noticed in under measurements, and just I wanted to show you that in this case we have something fine, and in this case we have something fine, and you see that this spectral feature here, it's very characteristic. So let's go to MERTIS and the moon. So we had this chance to observe the moon during the Earth flyby. MERTIS is flying to Mercury with BepiColombo, and we had a Earth flyby, and we were lucky that our NADI view was blocked. But since we have a space view for calibration, we could observe through the space view. And this is something that we just started this time as a test, and it came out that it's a wonderful flyby opportunity. So while most of the instruments could not observe because NADI is blocked by the transfer module, we could observe the moon and 2 times Venus. And if you are lucky, we can observe Mercury in one of the next flybys. We could not because there was some constraint in flight dynamics, but we hope it's going to happen. MERTIS is a sort of double instrument, is a thermal infrared spectrometer, is an imaging spectrometer that covers 7 to 14. So you will see all these features that I was showing you, Christensen feature, Australian bands, transparency feature in the spectra. And then we have the radiometer, because of course we need to sound the surface temperature for calibration of the measurements. And as I told you, the flyby was 3 years ago. We are still working on the data because from such a big distance, our field of view was really a mixture of mare and highlands. And so we really got a lot of problems in calibrating the data because it's not a unique region. You cannot really easily calibrate. And so this is the work we are doing for helping this procedure. We acquired new lunar simulants from Exolid. Is a great company that sells simulants. We just got in touch at LPSC, and we were amazed by the quality of their products. So we bought all of the available simulants, and so we have lunar mare and lunar highlands. And of course, we are gonna measure them, and you will see that they show spectral differences. So this is already something important to take into account. That it's good to have more simulants when you're gonna observe such a mixture.
2 minutes.
Thanks. And what we are now going to do is, after we finish measuring all of them in emissivity, we're gonna prepare caps that contains just half and half. So half lunar mare and half highlands. This is something we can do in the lab because we already built those caps. So you have to think about an emissivity caps is something like 5 centimeter wide cap that usually contains powder. But in this case, we have a cap that is split in between. So we have really a thin metal separation. We can do half and half. So it's not an intimate mixture because it's not what we are gonna see on the surface of Venus, of the moon with MERTIS, but it's a sort of aerial mixture, and we're gonna experiment with this. So just my last slide on the conclusion. So we measured hemispherical reflectance and emissivity of 10 lunar samples, and of course we are measuring them in emissivity in under lunar conditions, so in vacuum and 130 degree, and we of course identified several spectral features, the Christensen feature, the respiral band in this spectral range that we cover with MERTIS. And we are comparing the measurements with MERTIS. I haven't shown anything here because we are still working on this, so we want to finish the job and then show you the comparison, because we want to have something like a final word on this. And since we now have new samples in the lab, we can do again the same job on emissivity reflectance, and we can do the error mixing that we think will gonna improve our match a lot. Thank you.